We now look at a new type of functions called power functions, and in particular we're going to look at their end behavior. So first we're going to define what power functions are. We're going to show some examples of power functions, even some examples they may not look like power functions at first. And then we're going to figure out the end behavior of some of the power functions. So a power function is not terribly complicated. It's a function with the formula f of x equals a times x to the n, where both a and n are constants. Actually, they look a lot like exponential functions, except for the constant and the variable change places. Instead of having constant to an exponent variable, you have a variable to an exponent constant. So here's a very simple-minded example. Here you have f of x equals 2 times x to the fifth. Here the a is 2, and the n is 5. So that's not so terribly interesting. Here's one that doesn't look very much like a power function at all. You can see the constant 5. There is a power of x, but the power of x is in the denominator instead of the numerator. So you might wonder if this is a power function at all. Well, remember, if you're dividing by x to a power, that is the same as multiplying by x to the negative of that power. So 5 over x cubed is equal to 5 times x to the negative 3. 5 is a constant. Negative 3 is also a constant. That's a power function. Here's another one that doesn't look like a power function at first. 2 times square root of x. The thing to remember is that when you take the square root of a number, that is the same thing as taking that number to the 1/2 power. So you have 2 times x to the 1/2. Again, 2 is a constant. 1/2 is also a constant. So that is a power function. So even though there are some weird examples of different kinds of power functions, we're not going to get into too many of the intricacies of them. We're going to focus on f of x equals a times x to the n, where n is not only not a fraction, but it's not even a negative number. So it's a whole number. All right, so recall what end behavior means. The end behavior of a function is what happens to the outputs as x gets really large, x goes to infinity, or x gets very negative, x goes to negative infinity. And we're going to look at the end behavior of power functions. So in particular, let's look at the power function f of x equals x squared. Now, one way of at least getting an understanding of what the end behavior might be is to look at the graph. And as you can see in this graph, as x goes to infinity, in other words, as you go all the way to the right on the graph goes uphill very fast. It appears that f of x is going to infinity as well. Not only that, it appears f of x is going to infinity faster than x goes to infinity because the graph goes uphill extremely quickly. As x goes to negative infinity, that's going to the left on the graph. You can see the graph is still going steeply uphill, right? So it again appears that f of x is going to infinity on that side as well. So whether x goes to infinity or minus infinity, it appears that f of x goes to infinity, and that is just interpreting it from the graph. Now, what if we wanted to verify this? Well, we can't verify this by looking at the graph, because you can't look at the graph all the way out to infinity or negative infinity. I don't know anybody who can draw a graph that big. So what we're going to do is analyze the behavior of the function analytically and algebraically and computationally. Okay? So what we're going to do is we're going to imagine x getting very big, and then we're going to imagine what's happening to the outputs, because we know what the outputs are. If the input is x, the output is x squared. So what happens when we put a very large number in for x? What kind of output do we get? Well, remember, x going to infinity means x is getting really big without bound. X can get as big as you can imagine, and even then, even bigger than that. Well, when we square x to get x squared, that's still a big number without bound. In fact, it's even bigger than the x. If I square 1,000,000, it's going to be way bigger than 1,000,000. Which means that x squared is going to infinity as x goes to infinity. And therefore, the outputs go to infinity. So we can use the similar kind of reasoning with x going to negative infinity, except there is a little twist. So first of all, this case, x gets really big without bound, but it's really big and negative. So it's big in size, but not big as in being positive. So what that means is when you multiply x by itself, it's going to get very large in size, much like we did when we were squaring positive numbers. But not only that, but when you square a number, any number, you're going to get a positive number. Any number that's not 0, you're going to get a positive number. So if you get a very negative number, you square that, it's going to be really large in size. It's also going to be positive. So what do you call numbers that are getting very large in size and are also positive? Well, that means x squared is going to go to infinity. All right, so you're going to do some similar analysis on other power functions, and in fact, you're going to find a nice little pattern about what the end behavior is for x to the n when n is a whole number. And the name of the file for those activities is power function n behavior.